Talk to us about the VLT Pioneer Survey of T-Tauri disks in the Southern Hemisphere.
So, do you hear me? Wait. Okay, do you hear me? No? Okay. So, I'm Fabien Anthonioz, and today I'm a second year PhD student, and today I will present you our result on the VLTI Pioneer Survey on T-Tauri disk on the Southern Hemisphere. So, that survey has been motivated for several reasons, one of them being that the near-infrared interferometry is a very powerful tool which is able to resolve the innermost part of the young stellar objects. So I will explain you shortly the principle of the near-infrared interferometry. So we combine the light of pairs of telescopes, and we measure the values of the interference fringes on those lights. So here So here you have a visibility profile. So the visibility is scaled at the visibility of 0 meter baseline. So a visibility of 1 meaning that the object is fully unresolved as a point-like source, and the visibility of 0 meaning that the object is fully resolved. And the baseline we got here probe the different structure of the disk. So the short baseline probing more the large scale structure on the disks, and the long baseline seeking more the details of that object. So for the brightest big stars, that techniques, it's very powerful, it's very nice. And the data is rich enough to do some image reconstruction, as you can see in that image, which is a part of the work of Jack Luska. And one of the main advantages is that all that image is comprised in 1 nacopixel. So it's a very powerful technique to have all the detail of the inner part of the disks. But for the fainter T-Tauri stars, that observation are much more challenging. So the first interferometer weren't that sensitive, and so the T-Tauri stars weren't very observed. So as an example, I give you there the survey of Ekeson et al. Of 2005, which gives you which was at the time one of the most complete survey of T-Tauri stars. So you can see that there's very few stars, and that the visibility points are only one visibility point. So that's very few data. So for few data, simple models have been built to model those data. So as the Gaussian model for the partially unresolved disks, and particularly the ring model for the disk where we can resolve the inner ring model, the inner rim. So the ring model is based on the assumption that all the near-infrared emission is coming from the inner part, the inner rim of the disk, thus creating a bright ring around the stars. So the advantage of that model is that if one can adjust the visibility data he got, he can directly derive the inner radius of that disk. So and that radius is quite consistent with the expected sublimation radius for the brightest stars, but then it's become more complicated for the less luminous T-Tauri stars. So there have been several studies which aim to add new physics and sometimes new exotic physics to understand such a large hole in the disk. And in Grenoble, we went back to the basics, and we tried to fit that visibility point with a full radiative transfer, which is a full thermal and a full anisotropic scattering transfer model. So, and that model is constrained surprisingly well the inner ring radius, which become quite consistent with the sublimation radius for all the luminosity. So that is easily explained by the fact that the scattered light becomes the main emission process for low luminosity star, and if one wants to fit that disk with a ring model, the calculated ring model will be much larger than the only thermal emission of that disk. So we got a very nice model which has the other advantage of having some observables which are very different of the ring model ones. So as the visibility profile is much shallower, and we got a rapid decrease at short baseline, which is caused by the fact that its extended bright scattered component is becoming its result very quickly at short baselines, and thus that is associated visibility profile tend to zero very quickly. So, as I said, we have a very nice model which has quite different observable than the ring model, but we did not have enough data to prove or rule out that model until our survey. So that survey consisted on 20 nights over 2 years, from autumn 2011 from spring 2012, and it has been carried with the visitor instrument Pioneer, which is a 4-telescope combined instrument. That means that for each observation we got 6 visibility baseline. That is to say that we got 6 visibility points, and additionally 3 independent closure phases, which means that we got some information about the central symmetry of that object and the departure of that object. So we were not very lucky with the weather, with 5 nights lost due to the weather and very average condition for the remaining nights. But we managed to observe 22 T2 stars with quite long observation to have the UV plane turn a little, to have more constraint on the inclination and the position angle of the disk. And what we got with the data we have is that if we do a simple fitting with the eye, we can see that visibility profile is quite shallow, such as the full radiative transfer I showed you 2 slides before. And if we continue that line until the 0 meter baseline, we can think that the visibility at 0 meter baseline won't be at 1. It will be there's a rapid decrease at short meter baseline. But fitting with the eyes is not very scientist, so we did a quite qualitative model, which consists of a simple linear fit. And our fitting with the eyes were consistent, as you can see that the visibility at 0 meter baseline, it's below 1. So that cannot be because the visibility profile are normalized at 1. So there's a rapid decrease of the visibility profile, which is the proof that we got an extended component. So that's a first proof, a quite qualitative proof that our full radiative transfer model works, and that decrease at short baseline, it's quite common for all our survey. But then, as I said, it's a quite qualitative tools, so it doesn't work for binary, it doesn't work for edge-down disks or very bad data. It doesn't work too for unresolved stars, so stars with the visibility profile being equal to 1. So to have a more quantitative result, we did some modeling on our object. So for that, we took our object, some observable we can do, and we use the full radiative transfer code MC first. And so, as an example, I will give you the result we got for HT loop, which is a K3 stars with the spectrum revealing that there's some small silicate feature, and when we know that there is 2 companions on that star and 1 inside the disk. So with that assumption, we did a parametric model with an inner disk, a gap where the inner companion is lying, and an outer disk. And then we ran that model with the parametric with the radiative transfer code MC first. And so this is the resulting LCD, so the photometry versus the wavelengths, which fits quite well the data we got. And more interestingly, we did an image of that model that, and on our first step, we performed a Fourier transform over that axis to have that dashed visibility profile, and on that vertical axis to have the dotted visibility profile, which is quite consistent with the visibility data we got. So, in order to have a more refined model, we take into account the separation between the telescopes and the orientation of the baseline to have that refined model which is marked with the red triangle. So with that model, we can adjust the data and even reconstruct that little point which is caused by the orientation of the baseline, and we can fit the near zero closure phase, which is caused by which means that there is a little departure from central symmetry, which is caused by the anisotropic emission from the scattered light. So that would have been the end of my presentation 1 month ago. But interestingly, 2 weeks ago, we did a short survey of 7 nights with short baseline too, and we weren't very lucky with the weather. With the I know. With 75% of the night lost, completely lost, and very mean condition for the rest. We observed 18 stars, but only half of the data is exploitable. So, with the few stars we got and that we have good data, we did the same linear fitting as before. So, from the same star, we did the same linear fitting, and we can see that even with the addition of the shorted baseline, with that linear fitting with our eyes, we can see that there's always that extended component. The visibility profile the visibility at 0 meter baseline is still below 1. So when we zoom a little, we can see that we can reserve a little the extended emission there, and that means that with 10 meter baseline we can reserve that emission, which means that the bright extended component due to scattered light must be larger than 5 ARO for that star, ARO-P. So then as always we did some more quantitative results. So we run our model for HT loop, and our model has to be refined. We're completely underestimating that extended component. Our visibility profile is too high in respect to the data. So that's not that bad. We got new constraint to refine our model, which is great. So in conclusion, we can say that the scattering appears to be one of the main, if not the main component of the emission process in low luminosity young stellar objects, and that extended component due to the scattered light vary greatly from one disk to another. So this might be caused by different geometry on the disk or different grain or etc. We are working on that, so this is an ongoing work. So as a consequence of that importance of the scattering, the simple thermal model we had before cannot reproduce our more complete data. So we have to move on and to do more complicated model, such as the full radiative transfer. So in very summary, to have good model of titory disk, we need photometric data to have some fine to constrain the ACD, and then as much as near interferometric observation as possible, either in long baseline to constrain the very inner structure of the disks, and at short baseline to constrain more the large structure due to the scattered component. So thank you for your attention, and no questions.
Questions?
Ah.
Right there behind you.
when when you went back for the second observing run, just that, so is there configuration of the facility different to change the baselines, or is why did you get shorter baselines on the second set of observations?
Yeah, so the VLTI has the advantage of having four relocatable telescopes. So for that survey, we got the 80s telescope with the short configuration. So we managed to. So we take the occasion to constrain that extended component by observing at short baseline.
Any more questions? Alicia?
About how, sorry, about how the uncertainties on those points are computed and to what extent calibration uncertainties could enter in the absolute value of the visibilities?
Can you repeat, please?
Can you say something about how you compute the uncertainties that are marked on those points, the error bars, and to what extent there could be additional calibration uncertainties that would change the value of the visibility?
Okay, so the uncertainties of those points are okay. So our procedure to observe is bracketing the science star between two calibrators, and then we perform some 5 or more scans of two observations of 100 observations on the first calibrator, the science, the second calibrator, the science, etc., etc. So then the value of the visibility and the closure phase moving by the changing atmosphere. By the way, I can't tell you much about that uncertainties. It's directly reduced by the PNDRS pipeline, which is I didn't touch that program. So sorry.
All right. A last question? All right, then let's thank Fabien again.